All right, here we are in session 2, and today we're going to talk about linear regression. But before we dive into that, we're going to talk about models. So what is a model? When we say we're going to train a machine learning model, what exactly does that mean? Models are functions that represent our world, and they're really oversimplified functions. And what I mean by that is if we are trying to predict the weather, for example, we could probably be perfect at predicting the weather if we just had more data. If we knew everything that was happening all across the world at every second, and we captured all of that information and then we fed it into a machine, we could probably get pretty close to the perfect model, a real model that represents what is going on in the world. But you can see how that's probably millions and billions and trillions of variables. When I say all the data, I mean down to how the atoms are working in the world and interacting with themselves. So if you can just think about every single piece of information of everything that's happening in the world, then we could predict an event. So that is the real model. That is how that is happening. We don't have the information, the ability to capture that. We don't have the processing power it takes to do all of that. So we create these simplifications of the world, we create these estimates of what is actually happening. And that is what we refer to when we say a model. So there's this very famous individual, George Box, and he created this extremely popular saying within the field of machine learning, and that is that all models are wrong, but some are useful. So when we train a model and we create a model, it is wrong. It is not a correct, true representation of how to model house prices or how to model the weather. It will be wrong, but we can, if we know that it's wrong and we expect it to be incorrect, we can use it in useful and meaningful ways. So this is really important because sometimes we're working with stakeholders or we're trying to build something at work, and there's an expectation that if we just use AI, it's going to be all good. It's going to be 100% correct, and that type of assumption can put us in a really bad place. So coming from this foundation that models are oversimplifications of the world, functions that represent an oversimplification of the world. And so we're not trying to, when we're trying to predict house prices, maybe we're only trying to use 6 features. And truly, there are definitely more variables that contribute to it. But if we restrict to just 6 features, what is the model we're building from that? So it's an oversimplification. So to ground that in something maybe a little more reality, a little more useful, a model is a mathematical representation. Much of this can be boiled down to mathematical formulas, even the so-called black box machines, where we don't know how it makes this decision or how it makes the decision. It's just very, very sophisticated and chained mathematical formulas. And what it does is it maps input data to output predictions or decisions, and it makes decisions based on these patterns. So into the model, we tell it, hey, here's a bunch of examples of an apple, and we tell it that these are for sure apples. And we tell it, here's a bunch of examples of a banana, and that these are for sure bananas. And we do that with all of all these different fruit categories. What that enables the model to do is when we hand it a new fruit and we say, we don't know what this is, would you tell me what this fruit is? It will say with some probability that it believes that the likelihood of that fruit is an orange. It has a high likelihood to be an orange, and it will quantify that likelihood for you. So that's what a machine learning model does. It takes input in the supervised learning paradigm. It takes input with labels, and then you give it new input that it's never seen before, that's not part of your training set, and it doesn't have a label with it, and you ask it to recommend a label. So the purpose, what's the purpose of that? Why do people build models and train models? There are 2 primary purposes, and and this is as we're thinking specifically about supervised learning. There is predictive, where we want to make predictions, or otherwise referred to as inferences. If you're going to make an inference at time of inference, that is a prediction on unseen data. And there is descriptive models. So the predictive one is everything we've been talking about. We don't know what the weather will be tomorrow. Can you predict what the weather will be tomorrow? Descriptive is where we're asking it, we're training it over a lot of data, and then we're asking it to tell us which elements were most important in making that decision that it recommended. So we're saying, hey, I gave you a bunch of features about a house and I asked you to predict house price. Which features were most important? Which features influence the prediction of house price the most? Because maybe I want to do an upgrade to my house and I want to get the most bang for my buck. So if you can tell me which variables, is it bedrooms? Is it square footage? Is it garden in the backyard? Like which variables were most important in predicting house price, and that can help me quantify how I do my investments. So we can do predictive or descriptive. What variables influence that decision? There is a algorithm we'll talk about a little later in the course called decision trees, and decision trees output something called feature importance, and that tells you how important each feature is in contributing to the recommendation that it makes. So there are we started to talk about y equals mx plus b. There are three important components of a model. There's input data, and we will refer to them as features. So whenever, instead of calling them variables, you have an Excel spreadsheet and you've got those columns, and sometimes people call those variables. We're going to call them features. That's the nomenclature that you're going to see on the internet as you explore this field. And that is the information that we're using to make predictions. Now, something to know that's very important about features is that information has to be available at time of prediction. So if you're asking me to predict whether a claim is going to be easy to manage or not, or whether it's going to be complex, all of the information you give me has to be available at the time I'm trying to make that prediction. So I can't use notes that were later entered by nurse case managers to train my model if they were entered 6 days later or 10 days later after this claim was already closed. I can use that to help create my target variable, what I'm trying to predict, but that cannot be a feature that is input into my model. And I emphasize this because this is missed all the time. People go to build these machine learning models in production, they train it over a bunch of data, they go to implement it into an actual system or application, and then they say, oh, well, at the point in time we're actually trying to do this, that's not the data we have. This is the data that we have. So looking at not what your information or observation is about your person now, today, but really doing a historical snapshot. What did they look like at the point you were trying to make that prediction? So that's the feature, input data. The output is something called our target. So that's another nomenclature. When you see Y, when you see the Y here in formulas, that is our output. That is what we are predicting. It's typically in the form of a probability. So we're typically trying to predict like the probability that they are class 1 or class 2. And so you'll hear that referred to as our target variable. That's very common nomenclature. Then we have parameters. The parameters are the learned values, the learned weights of your model. So that's the magic sauce of how it makes that prediction. So in this case, when we have y equals mx plus b, y is our target variable that we are trying to predict. When we put in x, our feature, maybe that's height of an individual, we multiply it by m. M is our weight. M is our parameter of our model. We multiply it by the parameter that the model learned. And we add b to it. This is the bias, or this is the y-intercept. So adding, it's called y-intercept when you do y equals mx plus b, but when you start to get into machine learning, start to call it something called bias. So you can see these values on this map over here. So you can see that we put in x when x is 1, then we have the slope, you have m, so you take 1 times m plus b, and you get y. So this is our y equals mx plus b. So how do these models actually learn the parameters? How do they learn these coefficients? It's called coefficients in linear regression. As you expand to other types of models, it'll be called parameters. So what the models do is they leverage something called a optimization strategy or an optimization formula, and they figure out how to, based on that strategy, based on that reward policy, that incentive, what they do is they search through the space of the combination of these parameters and it's typically not in an exhaustive way. It's typically some type of greedy algorithm that's not necessarily optimized to give the exact best answer. But what they do is they try to find the best answer. What does that mean? So on the bottom here, we have like a parameter 1 and parameter 2. Let's just say, it may not make sense. I'm just going to say 2 things that have to do with the house, so forgive me. Let's say number of bedrooms. Somebody has 25 bedrooms over here. And let's just say square footage. Just, use your imagination that these numbers make sense. They do not. But let's say it's number of bedrooms and square footage. And if you take every combination of those, 1 square foot plus 1 bedroom, 2 square feet plus 2 bedrooms, in every linear combination of those, and then you map what the highest value is. So let's say this is your objective function. So let's say this is home price, and I'm oversimplifying here. And let's say home price is really high when you have, for some reason, 11 bedrooms and 20 square feet. Yeah, it doesn't make sense, but let's say home price is really high there, and for some reason it's really low when you have 15 bedrooms and 5 square feet. We live in a different reality. So what the model does one of the most important algorithms, which we're not going to talk about today in machine learning, is something called stochastic gradient descent. And in my example, I actually flipped it and I said the good values were up here and the bad ones were down here. So I'm actually going to call it stochastic gradient ascent for this. That makes more sense if I do the rolling ball analogy. Okay, so let's imagine the best values are down here and we're really trying to look for houses with low prices for some reason. And we don't want houses with high prices, or imagine the high prices are down here. Just the good things are down here, bad things are up here. This is not good. So maybe you start up here. Originally, how do you get the weights to start with? You have to initialize somewhere. You have to start somewhere. So you could initialize them randomly. So maybe we start here, or maybe we start here, or maybe we start here, or maybe here. So a lot of this is dependent on random initialization, and that's why setting seeds and making your computer do things randomly in a very consistent way is an important part of the scientific process for machine learning. We'll talk about that in methodology, but randomness plays a role in how your algorithm gets the same answer. So theoretically, if I didn't set a random seed, you could run the code, I could run the code, you could fall down this hole, I could fall down this one, we could get different answers even with the same data. I think that's important to know. But what stochastic gradient descent does is imagine you're a ball, and how do you find the bottom of the hole? You just keep rolling with momentum. So what it does is it looks at each of these points and it says, use this math and derivatives to say, what is the slope? Is it a flat slope? Is it a steep slope? Is it a really steep slope? Okay, keep going down the really steep slope. And so we can use math here, if we're at this point, to create arrows for us to say, what is the steepness and speed at which I would move this direction? What's the steepness here? What's the steepness here? And they are different answers, and it will choose the most steep direction. So stochastic gradient descent just says, keep moving down the steepest direction. So if you start over here, maybe imagine you're a ball, you would eventually land here. So it's a really cool algorithm. It's kind of how this works, basically. All I'm saying is you don't necessarily test every point. You test the optimization algorithm will make you test like some relevant points within the domain. By the way, this is a global minima and this is a local minima, which means it's a local means it's a low point, but it's not the best one. Our algorithms aren't necessarily optimized to give us the global minima. So we won't necessarily always get the absolute best answer, but we'll probably get a pretty decent one. And what this point would represent, the output of getting that answer is your weights. So then you would have, this is the value you multiply square footage by, and this is the value that you multiply number of bedrooms by to get your answer. Okay, let's kind of ground in something realistic here. So linear regression, I'm just gonna make sure everybody's added to the stage here. There we are. Linear regression is going to be our first machine learning algorithm that we talk about. This will be on your exam. This algorithm will be on your exam, and you definitely need it to do your assignment. So the problem is really no different than y equals mx plus b, so it's a really great place to start. And the foundations of this are really applicable into neural networks. So there's a reason we're starting with this one. You want to find the best fit line. So you have a bunch of data. You've got a bunch of data points, and really what you're doing is you're finding the line that averages those data points the best. And that is your best fit line. So when you look at the blue dots, that's your input data. When you look at the red line, that's your predictive model. So given an input of 20, let's go up to here, we would predict, I don't know, like 8, I guess, 8. Given an input, given 20, if the function f of x takes 20, y is equal to 8. That is our function. That's our linear function. You can see that it's wrong. It's wrong quite a few times. Do you see how many blue dots are not on the red line? Those are incorrect predictions. And the distance from the blue line to the red line is a more incorrect prediction. So it's a useful model, but again, it will be wrong. And that is okay. So this is linear regression. It's a supervised learning algorithm that models the relationship between the dependent variable and one or more independent variables. Remember we talked about y equals mx plus b. Here is your new exactly equivalent formula of that we will now be using for machine learning. So y, it stays the same, you're still y, equals, instead of b, we are going to use beta sub naught. So beta sub 0, beta sub naught. This is equivalent to b in your y equals mx plus b. This is your intercept, but now we will just always refer to it as beta sub naught from now on out. And your mx, x is still the same, except that in its one feature dimension, but your m is now referred to beta sub 1. And this looks weird for now, but I promise when we look at adding more than just one x to this, it will make a lot of sense. Technically, when you think about traditional linear regression, when I say traditional linear regression, I mean linear regression founded in statistics, because this is where it came from, statistics, and then it got evolved into the machine learning world. There's also something called epsilon. Epsilon is the error term, and it represents the randomness in the world. Remember when I said technically if we had all information, including how randomness worked, we could make a perfect prediction. Error represents that randomness. it's not real in your machine learning model. So you don't need to try to put error in it, except that one assignment that I have you putting error in for explanation reasons. But when you actually train a model, there's no error that's input into that. So your formula essentially gets simplified to y equals beta sub naught plus beta sub 1 times x. So this is our new formula we will be working from. You need to know that. Okay. So what does that mean? Let's try to apply this to something. If you give me how many years of experience that you have, can I predict your salary? These are two variables that have something called a linear relationship. That means when one increases, the other increases, and they do so in a linear fashion, which is kind of like this increasing line on this chart. A nonlinear one would be like a loop or something. So if you give me so salary is our y variable. That's what we're trying to predict. We're trying to predict salary on this, how much money you make on this y-axis. Beta sub naught is our intercept, and that is right here. That is when your years of experience is equal to 0. So essentially you can interpret, sometimes the beta sub naught has interpretation in the machine learning algorithm, and sometimes it doesn't, like it's hard to understand what it means. In this case, it's very interpretable. When you have no experience, how much money do you make? In this case, I set beta sub naught to 30. So that is your y-intercept. That's your beta sub naught. Beta sub 1 is for each year of experience, how much more money do you make? Maybe it's, I got to think of something that makes sense. Let's say $10,000 because it's an easy number to work with. So when you have 2 years of experience, you have $30,000 plus 10 times 2. So $20,000 plus 30,000. So now you make $50,000. If you have 10 years of experience, and remember our beta sub 1 is 10,000, it's 30,000 plus 10,000 times 10. So that's 100,000 plus 30,000. So now you make 130,000 with 10 years of experience. This sounds hopefully very simple to you guys, but this is truly how these models work. So this is the foundations of it. Now, let's imagine we have more than one feature. Let me see if there's a better, okay, I should have swapped these slides. Okay, this is a good representation. Let's imagine we have more than one feature. We don't just have your years of experience, but we have many other pieces of information about you. We have your zip code, we know where you live, we know your education, we know your education level. So do you have just a high school diploma? Do you have a bachelor's degree? You can see how as we add more information, we can probably get a better answer. So we're going to add more features, more X values. Imagine this is an Excel spreadsheet, okay? And you've got rows and columns. X11 is the first column and the first row. XM1 is the first column and the nth or mth in this case value in that column. So if you have 100 observations, this represents the 100th person and their first column value, their first feature. But you can have n features. Just like I said, we don't have to have one feature. We could have a ton of features. And each feature has an observation for that person. So this is kind of an odd way of looking at it, perhaps, but this is how it gets talked about when we move into neural networks. So this is important, understanding how this data is represented in something called arrays, and something really what this is called a matrix. If you look this up in math, in algebra, it's called a matrix, and algebra operations are what are used, linear algebra operations are what are used in neural networks. We won't talk a lot about linear algebra, but I think this is just a good point to start introducing you to a reasonable way to think about how the data is represented. Okay, back to that other slide. So, no, it's still not the formula I want. Sorry, I'm skipping. Okay, I didn't have one formula in here, which is the extension. I'm just going to do it on the fly. So let's imagine, since we have people online and I want you guys to be able to see this, I would normally whiteboard this, but let's just add a new slide. So let's imagine we want to extend linear regression. Oh, I do have this in here. I just have it later. I think I'm changing my... Okay, sorry. A weird ordering of slides. So imagine you want to extend it beyond more than one feature. I'll just touch on this formula and then I'll go back to where we were in the slides. What that would look like, the reason we don't do y equals mx plus b, because we want multiple n's. As we have multiple features, we have multiple things that we want to multiply by, a lot of multiples. So what we multiply square footage by is going to be a different parameter value than what we multiply number of bedrooms by or number of bathrooms. And so what you end up with is y equals beta sub naught, still the same, plus beta sub 1 times x sub 1, the value for what we would multiply, the parameter, times what the value was at number of houses, plus beta sub 2. Now this is our next feature that we're working with. And what's the weight that we're multiplying it by? And you can do that many, many times up to beta sub n, x sub n. So this is the true formula for linear regression. If you go to traditional statistics, they'll say multiple linear regression uses more than one variable and simple linear regression uses one. In machine learning, we just say linear regression and we just assume that you're working with more than one variable. So just so you know, but I put that in there for clarity. Okay, I did not end up needing that slide. All right, so if we're gonna generalize that and simplify that, because math likes to make things simpler, we would say y hat, the prediction that we are making, y is the ground truth, remember y hat is the prediction coming out of the model, equals beta sub naught plus the sum over all the parameters. So how many features do we have? Where x at j times beta at j. So this is the same as that other formula I had. They just took all those x sub 0, beta sub 0, x sub 1, beta sub 1, x sub 2, beta, and they just put it in a summation function. And they said, hey, there's 10 of these things, just loop over them and add them all together. So they just simplified that in the notation. Okay. If you get even simpler, if x sub naught is equal to 1, the formula just becomes a matrix product. So then this is where they start to use these types of formulas where you just do x. Remember when I said, I'll just say this one thing and then I'll stop going so deep on this. Remember when I said that this was a matrix? In machine learning, sometimes you'll see little x's and sometimes you'll see big x's, capital X's and lowercase x's. When you see a lowercase x, that means it's a representation of a very specific observation. This is an event that occurred. This is an instance of this. So if I had a little, these should all be little x's, by the way. This is a bad slide. These should all be little x's. A big X is a matrix. So big X represents the entirety of this data. So all of the columns and all of the rows. It's your entire Excel spreadsheet. So big X, whole Excel spreadsheet. Little x, one observation or even one column of an observation. Like it can be that niche. Why that's important is because when we move to talk about neural networks, and eventually if you guys continue into AI and you start talking about large language models and you start trying to understand the architectures under there, they will not write beta sub naught plus one, they'll just write X and weight. So they really like to simplify things, but X is your entire data set. And then B is just like what they're multiplying it by. So I think that's helpful to know for the future. All right, let's talk more about simple linear regression. So back to let me see where we at time-wise. Okay, 40 minutes. We'll see how fast we go here. So we want to fit points to a line. Well, how do we determine the actual line? Like we could draw a line anywhere. And sorry if I jump around in these, I just know I should reorder some of these. So if we have these 3 dots here and we drew a line here, how do we know that line is better than this line? Which line's better? This one or this one? Well, there's formulas that we can use, or this one. There's 3 lines. Should we do the red line, the yellow line, or the other red line? There's formulas that we can use to actually quantify that. So what we can, let me see, we're good here. So what we can do is we can use something called the residual or the sum of squared errors. And what we're going to look at is what did we predict? What's the value we said it was going to be? What was minus what was the actual value? So this is, and then we're going to square that. We're going to add those together for every observation. And that's going to be, that is our squared error, sometimes called the mean squared error. It's very natural if you think about it. So if you have a house price and you said it was going to be $100,000 and you said it was $150,000, we would take predicted $150,000 minus actual $100,000. That is $50,000. And we would square that value. Do you guys know why we have to square that value? Why wouldn't we just use the value as it is? It's a hard question.
You take me back to stats.
Yeah.
I learned it at one point and then forgot.
So fun fact, you guys don't have to know a lot about metrics. What we're getting into here just a little bit is because I want to build the foundations is metrics. This is about as deep as we will go into math for metrics in this course. There is a whole nother course. It's the second course, it's a follow-up, and we will literally talk just all about this. How do you measure these machine learning models? So we'll come back to linear regression, but and we'll talk about this more in there, but the reason you do that is because what if it's a negative value? So what if you predicted $50,000? Then your residuals might cancel each other out. So your model might say, I'm perfect, but it's always off by either up 50 or minus 50. So we square them, and that is our residuals. I won't talk any more about this because we talk about it a lot in the other class. Just know that is how we decide how the model is doing. There's a lot of other things I could say. So how do we actually learn that value? So this is the distance, right? This is y hat is our line. That's our model. And this is y. This is the ground truth. This is what the real value was. The distance between y and y hat is something called our residual error. So this is our residual error. This is how incorrect we were on that prediction. If we drew a line for each of these dots, how far away they were from the line, and then we added them all together, and then we squared them, that is the mean squared error. MSE, sometimes it's called. So that is how we know how correct our model is. So the mean squared error is what you guys will use for your assignment. You will not be tested on the mean squared error in this class. So you don't need, we just need to know how to score a model so we can do it in the assignment. This is the formula if you're curious. We'll talk more in a different class about that. So to answer my question about, and I'm going through some of these a little quickly, but the text is on these slides. How do you know which one is better? Well, we could calculate the values here. So let's do it for this one. There's 0, mean squared error is 0 because the predicted matches the true. It's 0, the residual 0, the residual is 0, but the residual for this one is 7. So you would take 7 divided by 3, and that is your mean squared error. For this one, you would take 5 divided by 3, because your mean squared error, or your residual is 0, your residual is 0, your residual is 5, 5 plus 0 divided by 3. So technically, this bottom line is better. And I don't know if I would have been able to necessarily tell that at a human eye. You could do a different line, and that is one that goes right through the middle. And that's a really hard thing to give to a human eye and say, is this middle line better than this one? But machines are really good at quantifying this. So this is 3, apparently, and this is 3. So now we have 6 divided by 3. So our best line is actually this bottom red one here. And we can quantify that, and we know that that's true. And that's what those models do, is they, you could think of it as kind of like tilting this to see which line would be the best, and then getting the errors for each angle. And maybe even to do the intercept. Okay, you found an angle. Now let's move it up and down and see which one's the best. My computer is going to die, so give me just 1 second while I plug that in. Okay, so that is linear regression. So I could ask you that on a test. I could see that. Which of these lines, and I could give you some numbers and maybe make it a little more challenging so you can't do it with your eye. Just so you know, in statistics, there are assumptions that come with simple linear regression and basic linear regression. And so you have to, in statistics, if you're doing this as part of a statistics class, you have to check all of these assumptions within your data. So you have to see, is the relationship between the features and the target a linear relationship? As one increases, does the other increase, or does it suddenly drop off? So one relationship that is not necessarily a linear relationship is number of seats in a car, because and maybe you're trying to predict the price of the car, because maybe originally in the beginning the really cheap cars have 2 seats, and then they have 4, and then you get more expensive and they have 6, but then you get really expensive cars and they have 2 seats again because they're all sports cars, right? And so you have these really nice fancy sports cars. That is not a linear relationship. So in traditional linear regression, you have to check for that. You have to check for independence. What independence means is that each person occurs once in the observation. And I know off the top of your head, you're saying, yeah, that makes sense. Like Facebook, you're one person, and Instagram, you're one person, and all these data, you're a claimant and you're one claimant. But that is not necessarily the true when you're looking at historical data. So what you looked like today and yesterday and the day before yesterday, now you're in my data set 100 times because I've got a snapshot of you over the last 100 days. That is not independent. You are not an independent representation of yourself 100 different times because you are related to yourself. So your data is related to yourself. So there are other variables in here. I could keep going through these, but I'm going to say that we will not use these in this class, and that they are not used in the field of machine learning. And I think a lot of statisticians would really disagree with that. But what happens is there is this law of, there's an actual law, and I am blanking on it right now, but this law of large numbers and basically this law of convergence that says that if you're working with really large data sets, anything over like 100 records, you can kind of like hand wave most of this stuff away, and you can just rely on your models being more correct, and it's going to converge to that correct. So if you're strongly violating one of these, your model performance might like reflect that, for example. So people don't address these as strongly in in machine learning. I just wanted you guys to be aware that they're out there. So as you're trying to look this stuff up and you see these assumptions and how you're supposed to meet them all, it's probably fine. Also, when you get into building and developing machine learning models, you most of the time don't even use linear regression. We're going to use more sophisticated methods. We're going to use random forests. We're going to use neural networks. So we're really only talking about this so that you understand the formula so we can apply it to other things. So not as much emphasis. Okay, two types of, I already talked about this, so I think you guys get this, but simple linear regression, like I said, in statistics was like one variable. So you're trying to predict house price based just on zip code. In machine learning, we just say linear regression, and we assume that you're working with many variables. But to a statistician, that might be called multiple linear regression. That's the formula. We touched on that. Limitations. Okay, we have 2 more slides. This is what I was saying earlier, where when you are looking to apply linear regression, it's not always a good model. In this case, yep, that looks like a linear relationship. X goes up as Y increases. This is not a linear relationship. This is like the seats in the car example, right? Where it's going up, and then it's going down. Not a linear relationship. You're probably not going to have a very good model. It cannot fit this data. It's no matter how you tilt this line, how you turn it, you can't make it bend. So it won't be a good fit for that data. This one is like maybe a slightly, this one's just showing that it's very impacted by outliers. So if you can see that the line is clearly here, right? But because we are treating every single point the same, this is a democracy or something. Everybody gets equal value. And so because of that, this point way off up here is pulling that line up because that average error is pushing that parameter up to be a higher value. It's trying to accommodate for that. It's trying to average across all of these. If you took that outlier out, you would have a straight line across here. So some people, if you do end up implementing a linear regression model, then checking for outliers is very important because they can be heavily impacted by that. Okay. Sensitive to outliers, assumes linearity between the features and the target. So for example, like the house prices, I assume as bedrooms keep going up, your house prices keep going up at that same rate. So if your value is 2 or $10,000, I think we said $10,000 a bedroom, I assume whether you add 1 bedroom to a 2-bedroom house or you add 1 bedroom to a 10-bedroom house, I assume it's both of those situations are going to go up by $10,000. It's not necessarily true, as we know, probably not true. 1 more bedroom in a 10-bedroom house might not have that big of an impact. So it's not always, linear regression has a lot of limitations. It's not usually well suited for complex relationships. However, it's very useful for understanding the foundations of where we start in machine learning and how we can understand logistic regression and then neural networks after that. Okay, I am going to stop the recording and then I'm going to ask you guys if you have any questions.